Okay, so I gave you this introduction about the electron microscope because we are going to go to EELS. So I just look at how many slides we have looked at. Is 40 slides, and we have 80 slides to go. And I'm not kidding. So, and before we go there, I show something that I can tell you that the EELS is back, and I want to show you something that I think is pertinent for this audience, which is, look at this. The triumphant return. So I found it on the internet, and I thought that was funny. Anyway, so the first microscope that had EELS was in 1944. I think the spatial resolution was of a few micrometers, and I think the energy resolution was also a few electron volts, tens of electron volts. And you can see now the electron microscopes got an energy resolution of a few milli-electron volts. Now, this I think was shown yesterday by Rohan. This is again a slide by Quentin and Demi. And then what you see here is the energy loss as a function of different energy regimes. So you have core loss, low loss, the ultra loss, low loss, which are the phonons, and gain in spectroscopy. Now, what I'm going to be talking about today is on the core loss spectroscopy. I'm not going to focus on anything on this area, but instead in the area here on the right-hand side. And then the idea, the logic here is, don't confuse me, man. How do we do EELS to quantify elements, oxidation state, thickness, and then other things that you don't think that it's possible with EELS, but it can be done. And today I'm going to show you some examples of that. So I think EELS changed and became a very important part of the analytical community in 1993, when these three papers that came out in Nature almost back to back were shown that you can have atomic resolution imaging with chemical analysis in the electron microscope. That was done by Nigel Browning, my PhD advisor, and Steve Penico, my postdoc advisor in Oak Ridge. And then David Mueller and Phil Batson from Cornell have a paper in the same issue of the journal. But why is this important and what became a big thing is because you can do chemical analysis, you can look at electronic state, electronic configuration, see the bonding of the materials Rohan showed yesterday simultaneously and with atomic resolution. That was the key, atomic resolution. So here I'm showing you an example that this is a spectrum image acquired by, this is by Julia Mundi, Hong Lin, and Rob Hobden in Cornell. This spectrum image took about 30 minutes to acquire. And basically the logic in here that you see the colors is for every single pixel, you have an energy loss spectra with core loss peaks. And then what they do is that they integrate the signal for every single element, and then they have the total intensity, for instance, for titanium, the total intensity for lanthanum, and oxygen, and then they just change it, they do a RGB map, and they show that as a plot. Now, this is an example that was shown by Rohan yesterday. This is a work that we did in Oak Ridge 13 years ago. And then you have here a silicon atom, three-fold coordinated in monolayer graphene, and the silicon atom, four-fold coordinated in monolayer graphene. Now, the bonding configuration of this happens to be that when the atom is four-fold coordinated, you have a depletion of the density of states on the L3 edge of silicon because the states are playing part of the bonding. While in the three-fold coordinated material, you have empty states because the electrons are not playing a role. But the important here is and what I mentioned is about aberration correction, is because before you will get in the papers, for instance, from 1993 with Nigel Browning and all those guys, the aperture size that they need to use in order to achieve atomic resolution barely with 2 angstroms was about 10 milliradians. okay? If you increase the aperture size, then the spatial resolution is going to increase. But the other thing that happens is that the current also increases, and the current increases with the square of the radius because it's the area. And then as a consequence of that, when you are able to get larger aperture sizes, right, of 30, 20, 30, almost 40 milliradians, then your current goes 10 times as much. And as such, you have the sensitivity to look at, for instance, the individual bonding of an atom. Now, the other thing that is important, and it has not been mentioned explicitly, is the scattering cross sections. So for an ADF image, so for the pixels that you see in here, this is the ADF image, this is EELS. So for every single pixel on that, we have a spectrum of EELS, right? These images usually acquired by about 16 microseconds per pixel. And the electrons go from left to right, top to bottom, 60 microseconds, depends upon the size of the image, in pixels, is about few seconds. To acquire the equivalent signal-to-noise ratio of a spectrum as the one that is in here, basically we had to average all the spectra, all the pixels that are in top of the silicon atom, and instead of having 16 microseconds per pixel, sometimes it has to be 100 milliseconds per pixel. Inelastic cross sections are very small with respect to elastic cross section, which is the part of the ADF image, but several orders of magnitude, 3, 4 orders of magnitude. How do we know that? It's because when, for instance, Jordan and Rohan were showing you yesterday about the zero loss peak, the intensity of the zero loss peak is 4 to 5 orders of magnitude larger than a phonon or than a core loss. So for instance, having a very stable helium stage where you can do images for a very long time is fundamental in order to be able to pick up signals in an elastic cross section. Now, in color spectroscopy, for instance, is the same thing as a EDX or X-rays selection rules. So for instance, a LH is a transition from 2p states to empty 3D states. Now, for instance, in the case of iron that I'm showing you here, you had the 2p states, and they got split into the spin-orbit coupling in p with a spin population of 3½ L plus J, and p½ L minus J. No, sorry, J L plus S, which is orbital equal 1 plus the spin 1½ and L equal 1 minus the spin 1². And that splitting on the core level is about 13 electron volts for iron. For other 3D transition metals, this splitting changes. For instance, for titanium is only 5 electron volts. For other materials, this is slightly different, okay? These usually occur white lines, spectra, and they look like this. Because originally, they were in the previous experiments on the electron microscope with EELS, they didn't have a camera. They have a film, sometimes Polaroids. And then these things will look as a white lines on the film. Now, how do you measure, for instance, oxidation state for a material as like iron oxide? I think in the 1980s, there were 3 papers, Richard Lehman, Christian Colliers, and another guy Japanese guy, I'm going to have the last name. Before that, they observed, especially Christian Colliers, observed that as a function of the oxidation state, so for instance, you look at iron oxide in the different oxidation states, then the ratio of the L3 and L2 peaks changes. So you can use that as a fingerprint to pick up the oxidation state of materials locally. In other transition metals, it works like that as well, but there is not only changes on the ratios of the peaks, but also shift in the energy of the peaks. And for every single material, for every single element, these rules have to be looked at carefully. Like, it's not like, one-to-one correspondence. But let me show you here, for instance, Kurata is the other guy who did experiments. So what you see here is 3 different compounds of iron oxide with different oxidation state. And then what I did is, the way, measure the ratio between this peak and that peak. And there are various ways to do this. One is just take the spectra and measure this ratio directly, the intensities, or take the second derivative of this spectra. And that was done by Gianluigi Botton in the early 1990s. When you take the second derivative of the spectra, you can think that this guy is a Gaussian, that guy is a Gaussian, and then the spectra comes from, let me go back. Where is it? Yeah, here. Here. You see here, for instance, this could be a transition metal, like for instance, the iron or whatever material. I think that will be lanthanum, N45H. And you can see that before the lanthanum, you have a decay. This decay comes from a power law, and it comes from the plasma region of the spectrum. So you can remove that decay, and it is called background subtraction. But this decay has a power law. When you take the second derivative, that power law cancels out, and then the spectra can just be, the intensity of the ratios can be just taken as the intensity of the peaks on the ratios of the second derivative. And by doing that, let's go here, boom, 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 here, you can measure the oxidation state. You measure the ratios, and you compare, okay, if I have iron oxide, and I'm very bad with these things, so Jaume is always correcting me. Which one is this one? Hematite. And that guy over here? Magnetite. You see, I'm terrible. Well, iron oxygen and iron 2 oxygen 3. I'm a physicist, I'm terrible. So, but the thing that is important is that these ratios might change just slightly, depends upon the collection angles and the convergence angles of the electron microscope. So what you see here, the difference between, for instance, the Collier's paper and my work is that it was taking a different microscope. But all these elements for these iron oxides were taken exactly with the same instrument, with the same convergence angles, same collection angles. And you can see that there is a very good trend of decreasing of the ratio, the L3 through H, from oxygen 3 to oxygen 2 to metallic iron, right? For instance, an experiment that we did many years ago is what happens with the oxidation state or the ratio between the L2,3 of iron and iron-based superconductors. These iron-based superconductors were discovered in 2008 by the group of Hosono in Japan. And then what I'm going to show you is one of the families of the iron-based superconductors, which is called the family 1111111. So for lanthanum, the rare element plus arsenic by iron plus oxygen, which is this one. This is the 1,1 family. And then there are different crystallographic orientations. So here you see I did the measurements for lanthanum. So the lanthanum atoms or the cerium atoms or the praseodymium atoms or the iridium atoms will be these bright atomic columns, and the iron arsenic columns. And then here will be in top is, for instance, lanthanum and oxygen on the column. And then here you have iron and arsenic in these very bright atomic columns. And you can see the thing that I showed you before, how the oxidation state changes. It decreases, right? Then you have the metal. And then for this crystallographic orientation, the oxidation state, kind of vary like that a little bit. But
the ratio is smaller.
Exactly. Yeah, you will see in a moment. Yeah. So the question is why the ratio is smaller in these materials with respect to the metal itself. Now, but look at this. This is giving a crystallographic orientation. Now what I can do is I can switch the crystallographic orientation. Right now I'm looking in the 010, and now I'm going to look at in the 001 along the z-axis. And along the z-axis, the thing changes even more. So you see how the lanthanum had a decay. Now what we can do is the following. I know the nominal critical temperatures, these superconductors, and I can correlate the temperature, the critical temperature of superconductor with the oxidation, with the ratio, the L2-3 ratio. And see what I get. So these are the numbers on the ratio for neodymium, praseodymium, Cu, lanthanum. This is metallic iron, which obviously is no superconductor, right? And you can see a very interesting behavior. Why is like that? It's because of the bonding, the orbitals on the d states, how they are bonded, and for this case is ultrahedral coordination. So I always get confused between the E2, the EGs are lower and the T2Gs, or is it the other way around?
It's octagon.
No, it's sorry, it's a tetrahedra.
Then it's G, it's higher.
So the T2Gs and the way that the T2Gs and the EGs are being bonded with respect to metallic iron. How do I do this? Okay, let me just go here. What does the L3 and L2 ratio depends on the oxidation state? For instance, this is not the case in X-ray photoelectron spectroscopy, where this radius is constant whatever the oxidation state and depends on the niobium, the NB, number of electrons involved in each Kroll level. What I will say that this was empirical observation.
Now you have to click with the mouse the screen.
Okay, click here, and then I go.
Now,
Yeah, so what happens here is depends upon the occupation number, right? The 3D orbitals are going to be more occupied or less occupied. And as a consequence of that, the L3 ratio is going to change. The L3 intensity is going to change, and the L2 intensity is going to change. And that is why the oxidation state is associated with the ratio of L3 is associated with the oxidation state. And I don't know why it happens in X-rays. I can tell you what else. Now, does this correlated with the superconductivity of the iron-based superconductors? And the answer actually, I do not know. Because all these measurements were done at room temperature. So the only that I'm doing is a correlation, is not causation, of how the oxidation is, or the ratio between the L3 and L2 is with respect to the nominal temperatures. So now that these new electron microscopes come along, one could go to the critical temperature and see whether there is a changes in the ratio between the L3 and L2, and then answer this question.
Yeah, because this was measured in the non.
Yeah, there's measured at room temperature. Yeah. In the electron microscope at the time, we could measure any temperature as long as it was room temperature. Plus minus 2 degrees Celsius depends upon how you put the temperature of the room. And I'm not making this up. My electron microscope in Seattle is at 28 degrees Celsius, because 28 degrees Celsius. And the reason for that is because the room, the air conditioning is not able to handle the temperature stability. So I turn off the air conditioning at all, and I let it to be to thermal equilibrium. And then the microscope room gets heat up because of the electronics. And then my microscope is a little bit warmer than the other microscopes. So my room temperature is 28 degrees Celsius. No, because nobody has done it at room. Nobody has, you didn't have a helium temperature. a helium temperature.
The TC is lower than the cuprates. Yeah.
Yeah. You need to look at the specific crystallographic orientations. Oh, people have not done it. It is amazing the amount of work that it is not done in superconductors because you didn't have the spatial resolution to look at. It is an open ground to look at around. There is so much work done in superconductivity in electron microscopy, but everything is at room temperature. Let's put it that way. So for instance, here I'm giving you an example.
So why do you need that atomic resolution here? Because you go to this experiment, you say XIS, no, at low T.
Because I need to know that the material is free of defects.
Yeah, but then you could have a material in which you know that it's superconductive, right? And then it's good enough to have no.
No, I don't. I disagree with that, because you don't know. Like one of the big problems, for instance, in YBCA superconductors is what? Defects, grain boundaries. How does the temperature changes on the superconductor when the material is pristine versus the grain boundary? How does the electronic structure is going to be changing or have defects?
No, I agree. No, it's not questioning your data. I'm simply saying because so far one could not reach low temperatures.
Yes.
Fields, one could at least do low temperature XIS.
Yes, they could do it. The other problem with these materials is that the grains are tiny. They're 100 nanometers, so 1 micron at most.
Okay.
So getting very clean samples was...
Okay, the integrated signal then doesn't...
And then notice one thing. The ratios depends upon the crystallographic orientation. So you will need to look at a specific crystallographic orientation because of the channeling effects. Here I'm going to give you an example, for instance, of an iron-based superconductor. This is iron selenide. The material is, a bulk is 56 Kelvin, and a single layer is 100 Kelvin when it's grown in strontium titanate. Now, it is believed that depends upon whether its growth, the termination is titanium oxide or is strontium oxide, its critical temperature might change. Now, the experiments have not been done in this instrument, in this material, but you could go with electron microscope, and because it's one single layer, directly correlate every single defect with its superconducting property, with the phonons that Jordan was showing, as well with the core loss on the iron. Things to do. Question here in the Chairman.
Yes, curiosity. So is the neon microscope is the only one that has proof atomic resolution at helium temperature?
No, I think the guys from Thermo Fisher are doing it as well.
Okay, so what is, because in ULIT they are installing several, for instance.
Exactly, that is the one. Okay. And then they are installing it.
Yeah.
So this thing is going to change in the next year, because now there are going to be instruments that will have that capability. This is an inflection point in the community.
Yeah.
We are just before.
No, because they are all installed also in user facilities.
Yeah. Okay. Let me move on. So this is the thing that we could. Oh, let me just click here. Okay. So this is a synchrotron, and then let me move on because I think what time do I have to finish? 12:30. Okay. Good. So a synchrotron. This is an Argonne National Lab. Big instrument. You have ALBA here. I have been in ALBA. Beautiful. Big thing, right? With respect to electron microscope. Now, one of the things that are important in synchrotron, for instance, is XMCD, which stands for X-ray circular dichroism, right? Why? Because you can measure whether a material is a ferromagnet. How do you do that? Well, they have they can change the polarization of the X-rays to right and left-handed. And depending upon the selection rules, then the material is ferromagnet, then will be a breaking of symmetry in the spins, density of states. So due to the selection rules, then what will happen is when you have a right-handed helicity, the L3 peak is going to be with larger intensity. And when you have a left-handed helicity, the L3 is going to be a lower intensity based on the empty state. So the L3 for spin up, larger empty state, so higher intensity. In this case, it has lower empty states, lower intensity. And the difference between the red and the blue spectra, which is this XMCD data, tells you whether the material is magnetic or not. And there are selection rules in X-rays, as well as selection rules with electrons, that tells you whether the material is ferromagnet and whether the ferromagnetism comes from spin and comes from orbit. In this case, for 3D transition metals, we know that most of the magnetism is spin driven, right? But the problem with synchrotrons is that state of the art, you get a spatial resolution, you are lucky, of 10 nanometers, 50 nanometers in both cases. So what you see here is like, this is the Department of Energy, 13 years ago. They have this, they bring all the experts on the world to tell you what is the thing that we need to do in order to make our synchrotrons better. And they say, we need to get better spatial resolution in our measurements. So this could be done with electron microscope. And for that, I have to give you a brief introduction of EMCD, which stands for either electromagnetic chiral dichroism of Peter Schneider, the guy who came out with this thing. They likes to call it energy loss magnetic chiral dichroism. I prefer electrons because we use electrons. So in 2003, Cecilia Herbert and Peter Schneider came up with a theoretical paper that they proposed a method in order to do magnetic measurements with electron microscope. And 3 years later, there was experimental proof of that thing. Now, one of the things, the main points that I want you to take with you is that you have to think that the polarization vector in optics, in light or X-rays, is proportional to the momentum transfer of the electrons. So if you can change the polarization of the X-rays, you can play around with the momentum transfer of the electrons, and you can mimic the momentum transfer of the electrons the way that you collect the data in order to mimic polarization. Okay, and if you do that, then you can do chiral measurements. And the rest of the talks is about this. So here's the first experimental data with X-rays, and then with EELS. And the idea is very simple in the paper, and I will show you in a moment why, is you have here an electron diffraction pattern that I steal from the internet. And so just for a schematic, you have an aperture size of more similar to, this is about 2 milliradians or so. You put your, you collect your L signal from this position, and then you collect an L signal at the same distance, but 90 degrees with respect to this position, and then you acquire another spectra. And if the material is magnetic, then the difference between the two spectra has to have this behavior that I showed you before, with negative and positive lobes in the L3 and L2 peak. Why is that? Well, what I'm showing you here is the cross-section of the absorption of light or X-rays. This part here is the Fermi golden rule, conservation of energy. This is your initial final state. And then here you have this E stands for the polarization of light. And you have here the constants of the absorption of polarization. And this is the double differential cross-section for electrons. And then what I noticed from here is you have, again, the same equation here, conservation of energy. You have here the same kind of behavior besides these constants in there, right? And the thing that is important here is that the physics mimics the same. Here you have polarization of light. Here you have momentum transfer. For circular polarized X-rays or light, what you will have is X plus IY. For momentum transfer, you will have Q perpendicular to Q prime. And that is it. So if you know how to do the experiments, then you will be able to take magnetic chiral signals. So what I'm going to show you, and then that is why I show you all these things in the first part of the talk. How can you do these measurements using aberrations? Okay, how do we do that? Well, we have a paper a few years ago, almost 11 years ago, where we discovered that if you use a non-uniform phase distribution of the electron probe, you will be able to pick up a magnetic signal. And here I'm going to explain you why is that. And that is what I gave all this talk in the beginning. This was an idea by Jan Roos in 2014. The interesting thing about discovering the PRL is that the paper got rejected 3 times from PRL. They told us, peace off, go somewhere else. And then we just say it was a mistake. This figure needs to be changed. We send it. The paper got accepted a week later. And then a week later after that, they told us, by the way, the paper got a cover of PRL. And we were like, Jesus. Since then, every time that a paper gets rejected, then we submit it again and it goes through. I call it a Jan Roos approach because he was the one that pushed it to go through. So the question is not about correct or not correct, but how to correct. This is the aberration corrector, the first one that had atomic resolution images with sub-Armstrong resolution in Oak Ridge, and that is my hand. And then this thing that you see in there is a cross-section. Here, there are tons of octuples, quadruple lenses that make the aberration corrector. So here the idea is that when you have a perfect electron probe, it will be like a nice airy or like a Gaussian light profile, very small. But as soon as you have aberrations, then you will have your electron probe will be thicker and you will have tons of tails in the electron probe. That is equivalent to have a laminar flow in water, for instance, in a fluid, and a turbulent flow in a fluid. When you have a turbulent flow, it is not anymore a small, tiny thing from the water. You open the faucet a little bit more and it's turbulent, and then the water goes and splits everywhere. So it's the equivalent to have like something that it goes like that, right? Humongous amount of water goes everywhere. But if you go to the edge of this cliff and you look at down, what you will see, you have tons of eddy currents. And eddy currents are going to be left-handed and right-handed. And you can calculate, for instance, the vorticity, the strength of these eddy currents in specific positions. And then what we do is we utilize these positions in order to make the measurements. And this is an idea that it was stalled from optics. In 1992, it was proven that you can have this thing that's called optical vortex beams. And then they are used for tons of applications, for measurements, telecommunications, and fundamental physics. And why? Because they carry orbital angular momentum, and I will show you then in a moment why. So how do you create a vortex beam? Well, you can use a holographic mask. And here, this is a picture taken from a Beckman-Moran paper in 2011. So you have a holographic mask, you have a plane wave illumination, it gets diffracted, and you will have these diffracted beams, and these ones carry orbital angular momentum. They call Laguerre Gaussian modes, and I'm going to explain you how this thing get arise from these holographic masks. The concept is very simple. We saw that earlier today with Sophie's talk. You have here a double slit experiment, right? You will have interference, and that interference is going to depend upon what? The distance between these two slits at the wavelength of the light, and you will have troughs, with higher intensity when the phase of the two plane waves are the same, and 0 when the phases cancel out. Now, this is, imagine that you have an incident electron probe that goes to aperture of 100 micrometers, but it has that kind of a shape. Mathematically, how you describe this shape? Mathematically describe this shape by this, cosine of L5 minus AR cosine of phi, where L is the number of dislocations that you're having here. So in this case, you have one dislocation, and this will be cosine of phi. If there will not be dislocation, you will be straight lines in here, and then this will be just AR. Now, the question that I have here is, how do we obtain the diffraction electrons by the mask? How do we do that? When you have the electron microscope, what it works is, for instance, you have an aperture, you have a plane wave illumination. For instance, the lenses are somewhere over here, and the sample is somewhere in this distance. what is happening between the aperture and the sample, for all practical purposes, is in a far field approximation, because the wavelength of the electrons are a few picometers, and this distance is like half a meter, right? So it is way far, far away. So the electrons get diffracted from this position to that position. And in order to get the diffraction of an aperture, this is called the Fraunhofer diffraction, what do? You take a Fourier transform of that aperture. In this case, we had to take the Fourier transform of the aperture plus this function. And that is the thing that in order to solve the equation. So we are going to do that in a moment. So basically what happens, you can take this cosine and you replace it by what? But e to the I plus e to the minus I, where the minus I and plus I is the argument in here. So you see what I do here. This thing argument is somewhere over here. This is the positive part, and this is the negative part, and this thing is part of the Fourier transform. And then what you need to solve is solve this equation. But notice that the difference between this guy and that guy is that there is just a change of phase. So you can concentrate in doing one of these guys and solve it for this position, because the other one will have the negative values. So basically, this is the equation, and you have to solve this equation. You can solve it numerically, or you can solve it by just taking analytically or numerically. You do it analytically, what is going to happen is that you're going to have a solution that looks like this. You are going to have a phase distribution that looks e to the L5, where L is the number of vortices. In this case, only L is equal to 1. And you will have here a donut. This is a Bessel function of first order, first kind, or order L of the first kind, and it was going to give you a donut like that. Now, the cool thing about these vortex rings is they carry orbital angular momentum. How do we prove that? By just applying the momentum operator to this wave function. So we take that, we apply the momentum operator to this wave function, and you obtain something like that. And depends upon whether this here L is equal to 1, but it's equal to 2. Here it will be 2h bar, 3h bar, 4h bar, and so forth. That would be for a perfect vortex beam. Now, what you could do is you can integrate along this direction, and then go like this. And what you will get is a phase of 2 pi. But the other thing that you could do is you can calculate this vorticity, which is the curl of this phase, of this wave function. And when you calculate the vorticity, you will obtain something like that. So this is a vortex beam with h bar, and this thing has orbital angular momentum of +1, and this has orbital angular momentum -1. And the idea is that because it carries orbital angular momentum, then you can do the experiments equivalent to what you do with the circular polarized X-rays. But the problem is that these do not exist in nature. In the electron microscope, they cannot be able to be done. So how do we do this? Well, the way that we do that is by putting aberrations to the electron probe. So what happens if I have a 4-fold astigmatism in my electron probe? It's going to look like this. So this is a little bit of astigmatism, 4-fold astigmatism, and my electron probe has this Gaussian phase distribution, but it has all these tails in there. But notice that the phase of my electron probe, and look at the perfect vortex being, ideally, that does not exist. If I zoom in there, in one position, you can see that it has the same phase distribution. The difference is that the phases are, you have positive helicity and negative helicity within the same phase, like that. So here's the part that the kick, or the whole thing, is that you can do measurements where you make these vortices hit atomic columns, and then these vortices hit atomic columns, hitting the atomic columns, then you will be able to pick up the magnetic signals or any chiral signal for that practical purpose. In the paper, we calculated that when you do the magnetic, like EMCD signal, it correlates perfectly well with this vorticity that I'm showing you right now in the probes, almost 1-to-1. And this is, for instance, for iron with different thicknesses. The other thing that is important is the sum rules in MCD that's going to be seeing in a moment. Basically, you can tell whether a material has a specific magnetic moment coming from orbit or coming from a spin based on these some rules, which is basically is an equation like that. You have the intensity of the L3 peak, the intensity of the L2 peak. You take the differences on those things, and it tells you the ratio between the orbit and the spin. So for iron, for instance, this ratio is of 0.3%. So like, I don't know, 97% comes from a spin for the magnetism. So this is the probe intensity that I showed you before. And here is the vorticity. What I'm showing you this is because the probe intensity and the vorticity are a little bit shaped. Where? When you have the we have intensity, the vorticity is 0. So the vorticity has higher intensity between the tails of the electron probe. And what we are going to do is going to do spectrum images with this electron probe. So this is a sample that actually Jaume gave me. And then this lanthanum strontium manganese oxide, and I think it was prepared by you, if I remember correctly or not? No? Okay, sorry about that. But so you have lanthanum strontium manganese oxide. The lanthanum strontium columns are the really bright ones, and then the manganese oxygen columns are the dark ones. And the logic is the following. You pull your electron probe with an aberration, and then you look at there, and you can see that there are some vortices that hit the manganese columns in the top and the bottom when the electron probe is at the center of the lanthanum columns. I change the aberrations to -10 microns, and then if I do it again, you can see that now I have the blue, and then here's the orange. And then the idea is that you take the intensity, you acquire a spectra with these two electron probes, you average them out, and then you take the difference, and then the material is magnetic, then it should be a magnetic signal. And does it look like? This is the sample. This is the spectrum image. And then the lanthanum, so the manganese and oxygen columns are the dark ones, but I don't look at the spectra in the dark ones. I look at the spectra when I am in the lanthanum columns. And I do the same thing for two different positions with one aberrations and with the opposite aberrations. And what you obtain is something like this directly. No question?
If I look at your probe before on your image, when you're at the position of the atom, I don't know, of the second line, you're actually probing the atom of the line above and below.
Mm-hmm.
How do you correct for that on your scanning? Like, how do you know which atom you're actually looking at if you're not probing the one that you are actually going
Let me go back. Here.
Yeah.
So the electron probe is going to go with this distribution for every single pixel, right? And the only that I want that I care about are the pixels that are around the lanthanum column. Because when the pixels are around the lanthanum column, as this depicted in this schematic, those electron probes are going to have the vorticity hitting the manganese columns. Basically, that's it. If the electron probe will be on the manganese atoms, then I do not have a magnetic signal.
Okay, thanks.
Mm-hmm.
Suppose that the magnetization of your layer is perpendicular to the magnetic moment of your beam. What happened?
Then you cannot do the experiments.
But how do you know that the magnetization in your film is just is parallel to the?
In this case, the magnetization, this is a ferromagnet, right? It's a room temperature, and I have a magnetic field that is parallel to the electron beam direction. So the magnetic moments are aligned.
The magnetic field around. Okay.
Yeah. Yeah, so look at this. I'm here compared with the XMCD signal, not from the same sample, exactly the same sample, but the same material. And look at the intensity of the XMCD signal with the EELS. And look at the ratios that I obtain. 1-to-1 correspondence, what you expect with the XMCD. But this was done with electron microscope with nanometer resolution. And with a signal-to-noise ratio much better, because this was done not with a single electron camera, you should be able to look at atomic columns, individual atomic columns, and measure that directly. Now, yes?
Just to test, have you tried to calculate the MCD signal from when the beam is on the manganese columns?
Yeah, it doesn't, you don't get it.
It doesn't give any.
Yeah, you don't get it, yeah. You don't need to even calculate, you just have to measure it, but you don't get it. Now, here's another one. We talked about RIGS yesterday. So there was this paper 2 years ago by the guys in Switzerland, where they measured the chiral phonons on quartz with X-rays, with resonant inelastic X-rays spectroscopy. How do they do that? Well, basically, I didn't know this, my ignorance, but quartz is a chiral material where you have a tetrahedral coordination with a chirality or handedness and strong schematically in there. And the idea, the hypothesis of these guys was that that the chiral crystal would transfer orbital angular momentum to the circular polarized X-rays. And then if the atoms are shaking around with these chiral-like phonons, what is going to happen is in the X-ray absorption, for instance, states goes from 1s to 2p. The 2p states are going to precess and are going to be moving like this when the atoms are moving around. So they could go and do a calculation, find out in which parts of the momentum of the Bridge-Johann song the coupling of these chiral phonons is the strongest with the X-rays and do the measurement in that thing. So this is the Bridge-Johann song of silicon oxide. They look at this position Q1, which you can look at the paper is in that specific position in the Bridge-Johann song. And then from that position, they go and they calculate which part of these chiral phonons are going to couple the strongest with the oxygen KH. And then where is yellow is the strongest coupling. And then the idea is that they do the measurements with the X-rays, with the RIGS, at 50 millielectron volts and 100 millielectron volts, you will have a chiral signal. What does it mean? If I do it with polarized right-handed and left-handed X-rays, you will have a difference of the spectral signal that is different than 0. And that is the proof. Now the idea is, how do you do that with electrons? Or in its effect, how do you measure the chiral phonons affecting the core loss spectra of a material with electrons? So there is a paper, theoretical paper of graphene boron nitride. And then in the particular case of boron nitride, because it's non-centrosymmetric, you will have chiral phonons in particular positions of the Bridge-Johann song, in particular in the K and K primes points that is showing there. And then at particular positions of the bridge, for instance, 150 in this longitudinal optical mode, you will have the boron going in one handedness and the nitrogen going the opposite handedness. And then in the K prime point, the handedness about 151 will be differently. So my logic was you should be able to do this as long as you have a monolayer or odd layers, or odd number of layers in boron nitride because of the way that the boron nitride stacks. And if you go to really low temperatures, you have the energy resolution and the core loss and low loss, you should be able to measure this. And I did this in Oak Ridge National Lab. So how do you do that? I want to remind you first the difference between high spatial resolution versus momentum resolution, high momentum resolution. Here is the bronchogram with a convergence angle about 30 milliradians, right? For this one, it looks like that. All these guys overlap. You have high spatial resolution. Now, if you change the convergence angle, well, they're overlapping, and you change the convergence angle, it looks like that. Then you don't have high spatial resolution, but you have high momentum resolution. Heisenberg centered the principle in the microscope, right? So what I'm going to do is experiments like that with a small convergence angle, because then the Bridge-Johann song is perfectly there. So you have these the Bragg spots, and my Bridge-Johann song should be somewhere over here in the middle, right? And this, the credit goes to Jordan Hachtel. Yeah. If Jordan will not be here, I will take the credit out. So here is the experiment schematically. So you have the Bridge-Johann song, right? You have the Bragg spots. These blue spots are where you will have the K and K prime. And the idea is that the experiment, the way that we do it is simply very straightforward. We put a slot, and then I will be able to see where these black spots are because they are really bright. And then I measure at 1/3 and 2/3 of these positions, and I know where the K and K prime points are going to be. Very straightforward. This is how it looks in real life with the electron micros at 60 kilovolts, 1 milliradian, no configuration. So my K and K prime points are going to be somewhere over there. So here is the boron KH acquired with this high momentum resolution. This spectra took about 40 minutes of acquisition. Okay. You have the Bragg spot, another Bragg spot. This is energy, right? And then these guys are the two PCS states. And then what I can do is I can integrate along the momentum resolution, and I get a spectra like this. Now, if the material is chiral, and I pick up a chiral signal, what I usually pick up is precession of the PCS states on the boron KH. And that means that I should see, that was at least my hypothesis, I should see chirality coming from here, but not coming from there. So how do I do that? I take a spectra from these different positions, and I just integrate it, take the difference, and divide it by the sum. This is what I obtain. You can measure chiral signals with electron microscope, with momentum resolution, and with spatial resolution of 10 of the nanometers. You will not be able to do that in the synchrotron because of the size of the sample. What about topology? I have 7 minutes. One clear example of topology is the Hall effect. 1879, measuring Johns Hopkins University, gold material. You put current in this piece of metal, and then you measure the resistance in the perpendicular direction. When the material has a magnetic field, you will see accumulation of charge going from the left to right. Right? There are many families of these. You have the anomalous Hall effect, was discovered a few years later, and it was called anomalous because they didn't understand why you will have a Hall effect when there was no magnetic field. Then you have the families, the quantum Hall effect, quantum anomalous Hall effect, quantum spin Hall effect. You have exciton Hall effect, phonon Hall effect, Valley Hall effect, fractional quantum Hall effect, anomalous fractional quantum Hall effect. And in the case that I'm interested right now, that I'm going to show you is that you, with the microscope, you should be able to measure the orbital Hall effect as well as the spin Hall effect. I haven't measured the spin Hall effect, but we have measured the orbital Hall effect. But the experiments are exactly the same. How do you do that? Now, the problem with these two Hall effects is in the classical Hall effect, you have electrons that are being accumulated in one position of the sample. So you have charge, you can measure the resistance or the voltage. But in this case, they are charge neutral. There is no, you cannot measure resistance. You cannot measure voltage. So how do you do that? So there was a paper 2 years ago by a Korean group where they did that for titanium. The reason why it's done for titanium is because it's known that the classical Hall effect, the conventional Hall effect in titanium is null. And the spin Hall effect is very small. But theoretically, the orbital Hall effect should be very large. How do they do it? They use smoke, magnetic optical Kerr effect. And the idea is very simple. If you put a current, then if there is orbital Hall effect, there will be accumulation of orbit or orbital angular momentum in one of the faces of the sample. Then what you put is you put a laser, and then the laser will deflect slightly different due to the Kerr effect. And then you do the measurement. How much it will deflect it? Well, you can see it here, few nanoradians. And they do the measurement as a function of current, and then they have the detection of orbital Hall effect. How do you do that in the electron microscope? Well, we have a paper that is in review right now, and you can look at it in the archive. And I'm going to show you the latest results in order to address to the referee reports, not to the referee's comments. So the experiment is likely very straightforward. You have titanium. You put you prepare this with a FIB, in this case, in a protochip material, and you put the electron beam in one edge of the sample. Then you do the measurement in off-axis, so you put the EELS aperture away from the center beam, similar to what you will do with the EMCD data. and then you put current going from left to right or right to left. There will be two ways to do the experiment in this case. One of the ways will be you do put current going from left to right, for instance, going like this. You do the experiment, then you have measurement at specific voltage. Then you take the sample, you flip it out, and you do the measurement again. That will be one way, not a very good way. The second way is you have the current going from left to right, and then you just sweep the current at the same edge, and you do the measurement. And then the thing is that you don't know whether it will be a spin or orbit that accumulates there. The way that we do the experiment is here is the diffraction pattern that you acquire for the microscope, and then this is where we put the EELS aperture. And this is a scale of how big the EELS aperture was and how small this is like 5 milliradians in here. Now, let me see what I have here. If I have a spin accumulation, like in magnetic, like in 3D transition metals for iron, it should look like this. If I have orbital accumulation, it should look like that. And then I just have to do the measurement and see which one I have. If there will be a spin Hall effect, this is what I will see on the left-hand side. It will be orbital Hall effect, I will see something like that. This is that optical image of the sample. The sample was coated with alumina in order to avoid oxidation of titanium because titanium loves oxygen. So you have to be sure that it doesn't get oxide. And then the idea is that you do EELS in the top edge, and you do EELS in the bottom edge, and you can do EELS in the middle. This is how the sample looks in the SEM. So I think this is about 5 or 4 micrometers in width, and the thickness of the sample is like 30 nanometers. This is the intensity map of one of the edges, integrated from 450 to 470. So basically, I've integrated the L3 and the L2 edge. And then, because it's the top of silicon nitride, this is the silicon nitride, and then the edge is somewhere over here, and you can see the microstructure. This is each pixel is 2 nanometers, and you can see the titanium field. How do we really do the experiments? Is you put a voltage of 1.2 volts, for instance, and minus 1.2 volts, and you get a spectra that looks like this, integrated. But you can see that they are not exactly from the same position. So you can see this feature in here and that feature in here, but they are moved, they are shifted with respect to each other. Like this feature is not present in the sample. So you do cross-correlate, align it, and you get something like that. And once you have something like this, then you see that they are on top of each other for the different voltages. And then what I care about is integrated along the x-axis, and I see how the intensity of the EMCD signal changes as a function when I go into the field. This is the spectra as acquired for the 2 different voltages. And then what I'm going to show you is the subtraction of this minus this, as I showed you before. So like this. This is the spectra from the top edge. So you have a magnetic signal that it looks, our EMCD signal that looks 10 to the minus 3. You can see, and then the edge, the distance from the edge, this was calculated from the second derivative of the intensity in order to see the inflection point of the material. And then let me go to the bottom edge. It looks like that. The signal is a little bit weaker, 10 to the minus 4. And then we think that it's weaker because of the microstructure. The materials are not perfect crystalline, clear materials. But you can do these kind of measurements. You go to the middle of the field, and the intensity looks like something is there, but what I want to show you is the integration, the average of the whole signal. Here is the average of the signal for the top edge, for the bottom edge, and for the middle. Now, you can see something that is happening here that is funky. It looks funky. The red and the blue spectra have a very nice signal-to-noise ratio, while the green spectra has a very bad signal-to-noise ratio. Why is that? It's because the red and blue spectra were acquired with a single electron camera, while the green spectra was acquired with a CMOS detector, where the quantum efficiency is not as good. But the important thing is, when you go and you look at the statistics, you can see you have larger error bars, but it's 0, and look at the numbers of the integrated intensity.
How big was the titanium layer?
30 nanometers
30 nanometers?
thickness,
No, but how long from the top edge to the bottom edge?
5 micrometers.
All right. Was there any reason why you couldn't do a smaller titanium bar and do it all in a single acquisition?
So yeah, maybe, but the reason why we didn't even believe that we will be able to get the data. The reason why we do it like that is because we wanted to be away from the two edges do not talk to each other.
All right. Do you have a sense of, like, is there a good way to calculate how far those need to be away, or did you just do?
Orbital diffusion bond length. It is believed to be 3 nanometers. So up to 3 or 4 nanometers, the orbital signal should decay. But as you can see in our data, if I go back, we have orbital signal that is like, 40 nanometers into the sample. And then it could be even larger. We are not the only ones that we have done the measurement. Rafael and those have done the measurements as well. And they don't, I don't know how deep into the sample they go, but they seem to observe the same kind of behavior. And then we believe it's in microstructure.
Thank you.
So I 3 minutes over.
I don't know. The fact that you don't observe a decay of the magnetic signal inside the film could not be that be a fingerprint that the magnetization you are observing is due to the Ørsted field, due to the current flowing? Because you have a current flowing, so you have Ørsted field down, and your sample is under a magnetic field. It has some magnetic susceptibility, so it gets magnetized.
I believe that is not the case because we have done also the measurements on the with respect to the on axis, and then there is no, the signal is 0.
What means on axis? What?
So because you have a, like basically what we do is like you can measure the magnetic signal by putting the electron, the detector away.
Yeah.
But you can put a detector in the middle, and then you measure current. And then when we measure the current, which will be accumulation of current due to this effect that you're talking about, the signal is equal to 0. So that is why it's not that effect. Yeah, we thought about that too.
You did the question that I want to do, but I have another one. Why it's so different, the intensity from one edge to...
Excellent question. I think this is the first evidence of microstructure affecting the measurements. The grains are like 20 or 30 nanometers. So they will leak into current, and because the different grains, like the sample is slightly different, the top and the bottom, then we are seeing these effects.
Yeah, okay. So because I mean, I know that there are many papers, like 2, in which they are trying to correlate the structure with the efficiency of accumulating this moment. No, so maybe it can be a proof, no, of the influence of the structure, the microstructural properties to the orbital accumulation.
So the first thing that we are doing right now, we are repeating the experiments with a material that doesn't have crystals, but is a perfect thin film with atomic sharp interface, such a way that we can really see how the microstructure affects the material. And then I have more data signal that when you see oxygen in other edges, in other samples, the magnetic signal gets quenched.
So this sample was a lamella? No. It's a foil, no?
It's a foil grown in a sputtering growth in the silicon nitride membrane.
And how is it that one side is so different structurally than the other side? I mean,
because it's microstructural. Like the edges are not perfectly defined. Like you could see it is like when you see it, it's not like a perfect atomic sharp interface in one side, a perfect geometric interface otherwise. Like has a little bit of the grains are slightly different.
Just another comment on the error on the green the green data. No? I mean, first I didn't get the point why you acquired with 2 different cameras.
I don't have a microscope yet, so I had to go to different microscopes.
Okay, no, because we did similar experiments on other materials, and the problem is that we were also, I mean, we were a bit stuck, not fully understanding the phenomena, because also the region of the sample in which it was not supposed to observe, we were not supposed to observe any signal.
You observe signal.
we observe a signal with a certain symmetry. Like I don't know if I don't remember if it was pointing up or down, but I mean, we were able to reconstruct the two features, so the positive and the negative double peaks. But when we point the laser, not the laser, sorry, the X-ray beam on the region in which, for symmetry and for other stuff, it was not supposed to be present any signal. Of course, due to the the error and the subtraction rule, the subtraction procedure that you have to do, of course you obtain something that is similar, that have a similar shape. So the two peaks, whatever.
Yeah, so I'm showing you the best data, but I have more data that when this systematically gets reproduced like that. Okay. So, and then the thing that is important is that at the end of the day, whether the signal to noise ratios or the signal, you can see there directly in the data, how good, whether they are wide error bars. The other thing that is important to happen is when I tried to do the experiment, so I went to PNNL because I have a joint apartment there. I was going to use the spectra, and the K3 camera was down, which is the Electron camera. So I had to use the Talos to do the experiment, and then I have a CMOS detector, and then I got what I got. And since I don't have the microscope to be doing it all the time, so it's one day, move on.
Yeah. I mean, just to say that maybe if you average a lot, you can obtain a signal which is similar to the blue one, and so maybe not be so sure about the two. I mean, of course you're sure and it's perfect, but I mean, to me, having this very scattered error, I mean, it doesn't prove
that is not a scatter.
I mean, what?
That is not a scatter.
No, I mean the green.
The sigma, the sigma levels there are 5 sigma. No.
Yeah, whatever.
So
okay.
What it is.
Last question. Jaume said last question, so it's last question. Now, if you use the sum rules for the orbital momentum, as what would correspond to the signal you obtain to which orbital, to which magnetic moment would correspond?
It's just orbit, but it's just there's not a spin in there.
Pardon?
It's just not there is not a spin in there. Like I haven't done the sum rules, but everything will come from orbit. You ask me which orbits these ones come from, which the orbitals?
I mean, in principle, this signal comes from a current-induced magnetic moment.
Yes.
So how big numerically is this magnetic moment in terms of MU's atom, let's say? How big is it?
I was finishing analyzing the data when I was in Cambridge, so I don't know the numbers yet. Because, yeah, anyway, I think we should finish, right?
Yeah, the very last question.
Sorry for keeping you from that. So my question is, so in these kind of devices, you would have also a temperature gradient because the central part of your wire will heat up more, and when you go towards the edges, then you will have some.
I do the measurements of the center of the material.
I'm sorry?
I do the measurements on the center.
Yeah, but like you would have a gradient of temperature. So would it have
temperature gradient of what? Of the material due to the current?
Yes.
Yeah, but I calculated, we calculated how much current we are going, and it's like tiny with respect to the material.
Way to escape from this kind of measurement.
Yeah, but if I would have a temperature gradient and I do it in the top and the bottom, and then I got the opposite effect, the temperature gradient is not going to be.
But you will have an opposite temperature gradient because the temperature will dissipate towards the edges. So the gradient will be up and down.
The temperature gradient will be along the x-axis, not along the y-axis.
It will be along the y-axis. Anyway, so that's one. And the other case, so can you please go back to the device, the SEM picture of you have?
Which one?
The SEM, the microscope.
Jesus, which one?
This one, yeah, no, yeah. So could it be that because your contacts are coming from the top, you have an uneven distribution of the current?
They have what?
Wire? An uneven distribution of the current in your wire so that you have more effect on the top and not at the bottom?
Well, but no, I don't think so. I don't know. The gradient temperature is going to be like this. right? I don't think the temperature gradient is going to be like that. The current is coming through here. This is 30 nanometers. Temperature gradient of what is going to be?
No,
Kelvins?
the second question is unrelated. I mean, it's because the contacts are from the top, right? So did you do any like, I mean, you can confirm with some COMSOL, like,
So let me tell you this, what we have done is we can do transport measurements, right? We don't even have a classical Hall effect measurements in the material.
Yeah.
Yeah. So it looks like the only that I can tell you that it is the things that you're mentioning will not change the ratio of the L3 signal. That is not going to happen.
Yeah, yeah, ma'am. That's why I'm just asking.
I don't see any physics that the temperature will change the L3 and L2 different. Okay, so let me finish because people want to eat. I want to eat. So what I show you today is that we do imaging in order where two atoms are, and we do a spectroscopy in order to understand what we can do with materials properties. And then we can measure, I didn't mention thickness, but thickness is something that is done, chemical mapping, bonding, and then I do believe that you can do chiral measurements, magnetic measurements, orbital measurements. You can measure spin. These guys measure that you will be able to measure superconductivity, Gauss, phonons, and with that, I will have to finish. Thank you.
Well, that's another question.
Super last question.
Sorry. You can also see if you have atomic resolution in the decreased antiferromagnetic order.
I do have atomic resolution in antiferromagnetic order. I didn't talk about those things, but yeah, we measure. We have atomic resolution in antiferromagnetic ordering with EELS and with 4D stem. Yeah.
Okay, so let's take the speaker.